I said I was going for before. Well, we've seen how to define a format specification. We just build up these combinators. We get a proof of correctness, so whatever we get out of here is correct by construction, right? And so we've defined sort of this definition of what it means to be a correct by construction package of these two functions with some proofs. We've defined some compositional instances and shown we can build them together. And we saw very simply an example of how you can use tactics to automate this entire process. We can just hit auto, and assuming you have a sufficiently good hint database, Coq should be able to find it. And of course, there's little asterisks here because I left several definitions. I highlighted them for now, and maybe since we're done, we can just go over those definitions and we can leave early. And again, what can I say? Dependent types plus tactics for the win, right? This is sort of Coq. Coq solves all problems. Okay. Well, okay, so there's one problem here with this simple example I've shown so far, which is why it's called a simple record, is that the format I showed here, this binary layout, made several simplifying assumptions that don't actually apply to standardized or realistic binary formats in a way that I'm going to spell out precisely right now. And thus, while this approach in general is exactly what we're going to go for, it's going to require several tweaks, including addressing this question of bijectivity that was asked earlier. So, okay, as an example, let's tweak our format a little bit. So what about this example? So here is a new source data type, here is a new format, and here is a new decoder. So what have we tweaked here? We've tweaked a couple things in all three of these definitions. I highlighted the RFC definition, but you could imagine there's an extra sort of field in that ASCII art that I didn't want to draw again. So in the source type, well, it's nothing too exciting here. We've moved away from being a product to being a record. So this is actually an inductive data type that was defined by a user. It has the same fields effectively, except now they're named, and we can have accessor functions for them, which is pleasant. There's one other tweak here. Now the payload has gone from being a fixed width vector to being a variable length list of bytes. Okay, well, that seems all right so far. This seems fairly realistic, I hope. This has necessitated a couple of changes to our format. So, number one is now that we have a variable length payload as a list of bytes, well, we need to have some way to tell the decoder how many bytes they should be consuming from the packet when they get it over the wire, right? Because it could be anything. We no longer agree. We no longer know how many to decode. So here in the format, you will notice right after word, we're encoding the length of the payload as a natural number. There's a way to read this right here. Okay. Additionally, we're out of sync with the type now, right? In the sense before, the type of the format was very much guided by the source type, and we were encoding things of this product in the exact same order they appeared in the product. So we did the ID, and then we did the date, and then we did the payload. But here, it's not clear from this record. We'd have to reflect on the definition of this record type in order to be in sync. So we don't want to do that. And in fact, we don't really want to force users to write formats that are in sync with their source type. So what are we going to do? We're going to define a couple new combinators that'll alleviate this burden. So there'll be a sequencing combinator. That's what this ++ thing is here. And that does hopefully what you'd expect. It takes two formats for some fixed source type and builds up a composite format by sequencing them. And then we're also going to have this compose combinator. And what is that going to do? It's going to take a format for some projection, we'll have a projection function, of the original source type and build up, and so here's a projection function, here's a format for the codomain of the projection function, and here's a format for the larger function. So you can imagine, how is this format defined? Well, we'll just apply the projection function to the source data type and then format it with this other thing. So here, the word format is just going to use the ID accessor for this record in order to format the ID, and so on and so forth. Okay. Does that track so far? No questions. Okay, great. Okay, and of course we made some changes to the decoder as well. As I mentioned previously, now we're using the decoded length in order to parse the payload. So now the decoder is defined in this monadic style. It looks sort of Haskell-y, not too unfamiliar. So here we're going to decode the length of the payload, and then actually the decoder function for list is going to take that length as an argument, and then it's going to consume that argument as sort of fuel to figure out how many bytes to consume. And then when it's done, we need some way of reconstructing the source value, but we've decoded all these values already. We have the ID, we have the date and time, and we have a list, and we can just use the record constructor to glue everything back together. So that's good, that's great. I hope. So things are a little bit out of sync, but we could imagine we can write combinators for these things, right? Or these proof-carrying combinators. And indeed, you would expect that. But let's consider how this might work for the combinator for lists now. So let's look at this definition. I've done a little couple of tweaks to this, this package. Recognizing the fact that the format and the source type are sort of out of sync now, I'm going to make the format a parameter of this record definition, of the combinator definition. So now I'm going to take a format and a witness that that format is correctly decoded by something, and I will build, given those for this, the elements in the list, and I will use that to build up a decoder for an actual list, and for the format that's defined by using that, the formats for all the sub-elements. Okay, so maybe good so far. We can imagine writing some sort of decoder function that will use this length as a parameter. That's our fuel. But the question now is, how are we going to fill in the hole for this proof component? And to see why that's slightly problematic, let's look at the signature of this hole. Okay. So note now that this decode function is anticipating as input the length. This should be an len. I apologize. So this decoder is only going to return lists of length n, right, by definition. And now we need to show that that is an inverse, a correct inverse, or correctly inverts this format function, which has no such constraints on its source values, right? It could, this formatting function could take a list of 0, a list of 1, blah, 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 go on and go on. So this proof is going to be hard indeed to prove, because if we can't really show that for an arbitrary length list, this decoder will accurately decode it. And what's the intuition here? The intuition here is the problem with this format is that it's no longer a context-free format, right? The correctness of encoded data very much depends on the correctness of this payload. The encoded data is no longer completely independent, in the sense that proving this decoder correct very much depends that it uses the right parameter for this length. And in particular, it needs to use the length of the original source payload in order to be correct. And it's going to be dependent. So the correctness of this particular combinator cannot be established in isolation. It can only be established in the context of a larger format, which is sort of shame, because as we said before, what we really want are compositional decoders. So what we need are some sort of compositional context-aware decoder combinators. Okay, so how are we going to do that? Transformers. Maybe.
Unrelated, why couldn't you just have a sigma on the other one to say, you know, there exists some n so that way n is no longer global? So
the suggestion was, why don't we put a sigma on the list here, right? And then we will have this fixed vector. Yes. Wait, where did you want to put the sigma? Well, I think the answer to that question is that this will eventually boil down to essentially making this another vector. This will be a fixed length vector. And this n up here is going to correspond precisely to the n that's encoded in that vector type. So if you do a sigma list, length list equals n, morally speaking, that's the same as a vector.
Oh, I'm saying, yeah, but don't put that constraint in there, that the list would equal n. Right. So I'm saying let n vary, so there exists some n, right? Can we not do that? Can we make it local, so that it's a pair, it's a number, and this decoding with it, this format? Right. So that it's a dependent pair?
So I can't immediately recover if that's going to work from the description. My expectation is that, in general, the answer is that will not work. And even if it did, there's a slight problem with it in the sense that now we would, if we wanted this to work, we would need to take our source data type, okay, and we would put in a bunch of dependent types in it, right? And it would no longer, these dependent types would be an artifact of this encoding function. They wouldn't be intrinsically necessary for that particular data type. We would just be doing this to sort of jump through hoops just for this application. And generally speaking, why would we want to make users of our library have to jump through hoops? Let's make their lives easier. But we can talk more about this offline, if that's okay. Let me show you my solution. Or the solution that Narcissus takes. There are probably other solutions, and in fact, I'm sure there are. So here's my proposal. Well, this is silly. If we're worried about this, talking about particular restrictions on the source value domain when we're relating decoders to formats, why don't we just restrict this statement, right? Why don't we tweak the definition of our round trip property so it can sort of incorporate information about the source value into it. So, in other words, let's define this round trip property with an extra predicate p, and we'll just say the format, the correctness of a format, will only be considered with respect to source values that satisfy that property. In other words, for all source values s such that s satisfies p, provably, decode is going to correctly invert that format. Okay. This seems pretty straightforward, and this is good, I think, because now we can define our combinator for lists as follows. Okay, well, we're going to work our way down here. So now in our definition of correct format decoder, we're going to say our decoder is going to be correct, assuming that this list, the length of this list is actually equal to the length that you pass in. And now it should be pretty easy to prove this lemma. That this decoder is correct, because we're only considering the decoding of lists who have the same number of elements as was passed in. And we can write that proof and do it once and for all, and that's good. So we can actually define this and put it in a library and reuse it, which is pretty great. And in fact, this works for all other sorts of dependencies, right? And these dependencies actually crop up all the time in real formats. Again, in DNS, it's very common to take a tag representing the type of resource record, encode it somewhere in the format, and then many, many bytes later, you actually use that tag to decode the payload of that resource record. You can imagine version numbers. There are many different versions of different protocols, and how you interpret a particular binary string very much depends on what version of the protocol you're using, right? So IPv4 or IP version 4 is interpreted differently than IP version 6, so on and so forth. All right, many examples of this floating around. Okay, so this is good so far. So we figured out how to define these combinators sort of modularly, right? But now in order to use this combinator, we need to, when we're working our way through the proof, we need to make sure that our proof is like passing along this information so we can actually apply it and get this proof of correctness out. So how are we going to make sure that the sort of context about what's been decoded before gets passed down to subsequent decoders? And there are many ways to do it. Here's how we're going to do it. We're going to embed this in the combinator for sequence. And here I'm going to specialize sequence. So this is going to be particularly the case where I have a word, I'm formatting a word of some projection of the source data type, and then I'm following it with some other format, just for ease of presentation. We'll simplify, or we'll generalize this lemma in a little bit. So the key bit here is now, when I'm decoding, when I search for a correct decoder for the rest of the format, I have a restriction on the source value. And in particular, I have this restriction that this source value, this projection of this source value, is equal to the word that I decoded previously. That's what this is right up here. And actually restate that here. And this is just a recapitulation of what I said before. So this is the interesting bit here. So we have this additional restriction on the source data type. We're going to keep track of the previous context. That's fine. And then we're going to add this additional restriction that relates the value we just decoded at this step to the original source data type. So the best way to understand this is to see this in action. So I have an example here. So here, suppose this is a goal ncoc, and we're trying to synthesize an inhabitant of this type. Here's our simple record format. And here is the source restriction predicate. Here we're going to assume off the bat that we're only going to be decoding records whose payload contains less than 2 to the 8th elements. Why are we doing that? Well, if you recall, we encoded the length of the payload in an 8-bit field. And so in order to correctly recover all of the elements, we need to make sure that the length actually fits in that field. In much the same way in the previous talk, we needed to make sure that there were fewer than 2 to the 64 CPUs for pseudocode for that ticket spin lock, or ticket taker algorithm. Right, okay, so here's our starting state. Now, we could apply that word sequence decoder rule that we saw before, and what's the sub-goal we're going to get? Well, we need to find a decoder for the rest of the format, right? Under the assumption that we have some value in hand, W, and the ID projection of the original source data type is equal to that value. And imagining we have sort of sequencing combinators for the other base data types, we can just work our way down the format until we get to the very bottom. And here, what does this say? Well, this says, here we have the empty format. You can imagine that we were always implicitly appending the empty format to the end, right? And so now we need to find a decoder that can completely recover the original source data type given an empty string, which seems impossible in general, but we're in luck because at this last step, this predicate, this source restriction we've been carrying along the entire time has been relating this source value to the values we've decoded. So we have the ID, we have the payload, oh, here's the payload, and we have the timestamp. And what does this mean? Well, this means that this restriction actually restricts our source data type to be a singleton set, or a single value. These equalities uniquely determine what the source value has to be, even though we don't have any additional information in this string. And given that, we can actually see pretty trivially, just by looking at it, how to immediately recover the original source data type, because we just look at these equalities and we can reconstruct it using these values. Are there any questions? And not to give away the punchline here, but in fact, we can use LPAC magic in order to just figure out what this function has to be. And we can automate this entire process. Okay, so here's sort of a key bit here. One of the key bits here is we've defined these correct decoders in such a way that it's possible to, A, when we define them, capture exactly the bits of information that need to be placed in the surrounding format in order for them to be correct. And we've defined these higher order combinators, in particular for sequence, in such a way that it's threading information through as we're deriving a particular decoder implementation, which is pretty cool. Okay. Right. So I'm going to peel back the hood a little bit more on Narcissus, and you might be asking yourself, what do these base combinators look like? I've been using word format and word dec. Well, what if I wanted to write my own function, which is conceivable? One of the nice things about these Haskell combinator libraries is that it's very easy to write your own Haskell functions and incorporate it into the larger framework. So hopefully you should be able to do that with Narcissus. And the answer is, yes, you can do that. And in fact, your basic building blocks are just functional programs that have a monadic style. So our encoder for format, our format for words shouldn't look too unfamiliar to anyone who's been working with Coq all week. It's just going to, what is it going to do? It's going to match the word. In the case that it's the empty word, it'll return the unit.